Hello everyone. So remember last time we had our formulas for the accumulated value of an annuity immediate, where payments start at P and increase by R times 100% each period, as 1 plus J to the N minus 1 plus R to the N, where R is decimal, over J minus R, whole thing times P, which of course doesn't make sense when J equals R. And while you can evaluate as a limit, when J approaches R to get something concrete, let's just take a step back and see what we get when J equals R. So remember, without using the finite geometric series formula, this is where we ended off. Okay, so we have to evaluate this here when R equals J. Well, when R equals J, everything inside here is just 1. So, right, we just have exactly this, okay? And, inside the brackets, as I just said a second ago, it's just 1, okay? Well, we're just adding up 1 n times. That just gives us n. So it's a particularly simple, straightforward formula, Pn 1 plus j to the n minus 1. And what's particularly simple is a present value, because if we just multiply everything by 1 plus j to the minus n, okay, remember, as I mentioned last time, whenever you have an annuity and you, take the accumulated value, future value, you're dating everything to the end of the annuity, t equals n. Well, if you just multiply everything by 1 plus j to the minus n, you're dating everything all the way back to the start of the annuity, which is exactly the present value. That is, by definition, the present value. It's the time-valued, it's a time-valued sum of your annuity dated at the beginning of the annuity. Okay, so multiply everything by 1 plus j to the minus n, and you're left with Pn 1 plus j to the minus 1, which is just Pn new, where new is your present value factor. Okay, so so just something to remember. These are your formulas when R equals J. Nothing too strange about R equals J, but anyway. All right, so let's get into the other main, or at least another kind of, I don't want to say exotic, because there's really nothing exotic about this, but a special annuity situation. And this looks exotic and silly, but as we'll see, it's very concrete. So let's look at arithmetically increasing annuities. So what the hell does that mean? Well, we have an annuity immediate and periods as usual. Payments are P, 2P, 3P, all the way to NP. So that's just payments at the end of each period. For some, P are P, 2P, 3P, et cetera, et cetera. Interest per period is J. Nothing strange about that. So make sure we're all on the same page here. Here's the timeline. Excuse me, the first payment, first deposit, whatever, just P. As usual, that accrues n minus 1 periods of interest at a per period interest rate of J. So it's P1 plus J to the n minus 1. Well, the next payment is 2P. This accrues n minus 2 periods of interest, so 2P1 plus J to the n minus 2. I don't have it written here, but for the third payment, it would be 3P. That would accrue n minus 3 periods of interest dated to the end of the time valued at the end of the annuity. So it would be 3P1 plus J to the n minus 3. Keep going. You get n minus P accrues 1 period of interest. And then finally, NP accrues no periods of interest. Okay, right, so add everything up. So standard actuarial try saying that 10 times fast after a few shots. But anyway, so standard actuarial notation is IS, I for increasing. S, like I said, S is for future value. I have no idea why you pick S for future value. F would make more sense, but anyway. So this is standard notation for this increasing annuity situation. Okay. So factor out a P, right, and this is what we have to sum up. And if you want a good, interesting problem to do, try and come up with that. You add all these up and you get this formula right here. And this is quite nice because you can use our calculator to get S double dot NJ, no problem at all. And I'll sorry about that. I was converting another Zoom video while I'm doing this. So I'll actually do in a moment how to get SNJ on the calculator without anything here. The answer is, well, really it's kind of like a 1 in front of the SNJ, so you just set payment to be 1. But anyway, okay, yeah, so this is a nice formula. We can do this very quickly with our calculator. So what I want to do now is a typical application of this, and this is a really nice problem because this is a very realistic problem, just like the rent payment problem. It's a very realistic approximation to, how much you're going to have at the end of 20 years of paying rent. In the last video, where rent increased by, I think it was 2%. I forget how many percent. I think it was 2 or 3%. And then maybe, I think it was 3% rent increased per year. And then you invest into, right after you get rent payments, you invest into a fund earning 2%. Okay, so before I do that, multiply everything by 1 plus j to the minus n. Same thing as multiplying everything by nu to the n. Well, the future value just becomes the present value. N becomes n to the nu, n times nu to the n. So you have your present value. And again, standard actuarial notation, I for increasing. We'll actually see a decreasing version in the next video. But all right, so let me put this to good use. And I'll spend some time doing this example because it's, it's not immediate how to do this. Well, it might not be immediate. Maybe it is. So a person invests $100 into an account, earning 4% effective annual interest at the end of each year for 10 years. Okay. At the end of each year, just after the year's interest is credited, the person puts this year's interest into a secondary account, earning 6% effective annual interest. Okay, so right, so you want to just keep, let's say, the principal amount of $100 in the account, but well, right, so you keep adding 100 into the account, and you always just want to keep the principal amount at the end of each year in the account, but you want to put the interest earned for that year, into a secondary account. Because you might think, well, I don't really need the interest, so I might want to put it in a secondary account. And you might be saying, well, why wouldn't you just put all the money into a secondary account if it earns 6% effective annual interest? Well, realistically, that might represent your estimated return, investing in, I don't know, some index fund on the stock market. And there's really, realistically, especially now with, stocks going, I don't think anyone really quite knows what's in store for the stock market. But yeah, there's risk involved in the stock market. So you might think, well, okay, I'll be willing to, take some risk with the interest that I'm getting each year, but I still want my principal amount to just stay in this account earning, this CD or whatever. Probably not going to get a CD with 4% now, but this whatever account earning less, that much safer account earning less interest. Okay, so what's the total amount in both accounts? So the total amount in the first account is pretty straightforward. It's the second account that's a little tricky. So let's do this, okay? So definitely I would draw a timeline for this problem, as we will do right now. Okay, so let's draw a timeline for just the deposits into the first account, and that's very straightforward. There's really not a whole lot to that. Just a bit. Okay, so deposit. Okay, so this is going to look a little different than usual timelines, but I think it still should be very clear. So I'm going to write up to 4 to absolutely make sure the pattern is apparent. So we're doing this for 10 years. Okay, so so all we're doing is depositing 100 into the first account at the end of each year. Okay, so let's down here write the total in the first account. Not a lot to that. Here it's 100. Well, add 100 to that. Remember, we're taking interest and putting it into the second account. So there's no interest added into this first account because we're taking that interest and putting it into the second account. And we'll get to that in a second. But so we just add another 100 because we're adding 100 each at the end of each year. So it's 200, 300, 400, and not so surprising, 1,000. Okay, so now this gets a little interesting. So let's look at the interest deposited. So I'm running out of room, so interest deposited into second account. Okay, so so well, there's no interest from 0 to 1 because there's nothing in the account. From 1 to 2, so right before the deposit of 100 at the end of the second year, the account earns 4% effective annual interest. So this is going to be, 100. So putting this year's interest of $4 into the second account. Okay. Now let's do the same thing for years 2 to 3. Okay. So there's 200 in the account from 2 to 3 right before we added 100 at the end of the third year to get 300. So that 200, it's still 4% interest. So it's 200 times 0.04, and this is something you really want to remember. I want to write this as 2 times 100 times 0.04. Because this here, well, it's kind of silly to write this, but well, it's so, yeah, just to maybe make it, I mean, you don't really have to rewrite this, but this is my P here, and this is 2P. Let's do this one more time. It should make sense what's going on now. From 300 to 400, we earn 4% of 300, that's how much is in the account. It's right. Yeah. So without interest credited, that's how much is in the account right before we credit the account for that year. Right after that, we put in the 100 at the end of the fourth year. So it's 300 times 0.04. So this is going to be 3 times P. So this is largely why we study these kinds of problems. This is why we largely study increasing annuities, because they occur very naturally when doing problems like this, where you leave principal in the first account and just deposit interest into another account. So I just want to move this 2 over. Do a better job writing that. There we go. Okay, so you can see the pattern here. It's just when you have a 4 here, it's 3. When you have a 3, you have a 2. It's 2 here. When you have a 2, it's really a 1 here. So it's 100. It doesn't look like 100, but that is 100. So here it's going to be 9. Sorry. Let me erase that. So it's 900 times 0.04. So you can probably get away with this for 10, but if I had it for 30 years, you really don't want to enter 30, do 30 computations on your calculator by hand. And you cannot use Excel in this course. So I think I allowed people to use Excel, but I have nothing against Excel. As an actuary, you actually use Excel probably on a daily basis. You'll almost probably learn to get quite intimate with Excel, maybe more than you would ever want to or ever dreamed of. But yeah, for this course, I don't want to use Excel. So you can probably, I'm sure you can maybe do this problem easy on Excel, but the point is not to learn how to use Excel. It's for you to understand how annuities work. Which again, I don't want to belabor this point, but if you don't, then good luck passing exam FM. And still, I think even if you're an economics student, it's important if you have any interest in any quantitative finance whatsoever to understand quantitatively annuities. Okay, so anyway, enough of that. Yeah, and just to make sure everything is clear, so I'll just put, So just draw dots here. So this is at the end of the second year. So one little tricky thing that often gets people, and don't be that person who screws this up. So this is not a 10-year annuity, because here, remember, there's nothing here. So it's just a big fat 0. Okay, and of course there's 0 here. This is a 9-year increasing annuity immediate. It's not 10-year, it's 9-year. Because again, from 0 to 1, there's no interest. You didn't get any interest because you didn't have anything in the account from 0 to 1. You only first put money into the account at the end of the first year. Okay, so right. Okay, so anyway, now after this timeline, this is fairly plug and chug. So let's do this here. So, right, so, so accumulated value in first account, well, we already got that. That's just 1,000, not very interesting. Okay, so let's see what you got from putting all the interest into the second account. It's not nothing. It's a decent chunk of change. So like I said, it's a 9-year annuity. It's not a 10-year annuity. It's 9 years because it really kind of starts. Maybe I should put the zero. Well, I'll put the zero also down here. Kind of silly to put equals 0, but right. So it's really 0 here. So really, the annuity starts at t, or the annuity payments start at t equals 1. The first payment essentially deposit into the second account starts at t equals 2. So it's a 9-year annuity, and I don't want to sound like a broken record when I say that, but most people, a lot of people screw that up, if not most people. That's been my experience teaching this. This is my 3rd time teaching it. So, I mean, it's not a huge deal if you screw it up in this course, but if you screw it up on exam FM, you know, one problem could mean the difference between pass or fail. And these are not particularly hard problems, in my opinion. So anyway, J is the interest rate for this account. We only used, we only used the interest for the first account to figure out what the deposits are into the second account. This 4% does not play into our formula for the increasing annuity. What we use from that formula is 6% effective annual interest. All right, so let's get back to the whiteboard here and finish up this problem. So what we have here is this geometrically increasing annuity. The first payment is, well, P is just 100 times 0.04, which is 4. So if you want, you can write on your time diagram that the first payment is 4, the next payment is 2 times 4, 3 times 4, all the way up to 9 times 4. So let's plug this into our formula for an increasing annuity. So IS 9.06 is equal to P 4 times S double dot 9 J. J is 6.06 rather, minus N, which is 9, over 0.06. And let me pop this into my calculator real quick. Actually, pretend you didn't see that. So, yeah, so I'm in begin mode. That's good. Double dots, you always have to be in begin mode. 9N, 6 interest rate, nothing in front of the S, so we'll make it a 1 minus for payment. Compute future value, minus 9 over 0.06 times 4, and we get 212 and 5 cents. Okay. Yeah, and that finishes up this problem. This is the accumulated value in the second account after this 10-year period.